We have seen that given a vector space, a basis is a collection of vectors v1 up to vn such that these vectors are linearly independent and they span the whole vector space. Then the span of that set is the whole vector space. We have seen that we can find many bases for the same vector space. In this video, we will show that if we have another basis, t equal to w1 up to wm, then the number of elements of the bases must be the same. Even though a vector space may have infinitely many bases, or actually E always have infinitely many bases, the number of elements in each one of those bases must be the same. Then the theorem says that if B and D are bases for the vector space V, then n must be equal to n, and we will use this theorem to define the dimension of the vector space. M, which is equal to n, is equal to the dimension of the vector space V. Notice that in order to find the dimension of a vector space, we just need to find a basis. That means we need to find a collection of vectors that are linearly independent and span the vector space, and we just count the elements in that basis. That's the dimension of a vector space. Let me start showing this theorem for a very particular case. Let's suppose that we have a vector space and somehow we know that v1 and v2 is a basis, and let me show you that it's impossible for three vectors w1, w2 and w3 to be a basis as well. Then the way I'm going to do it, I'm going to show that if this is a basis, then these vectors must be linearly dependent, and therefore they cannot be a basis. Then how do we do this? Since B is a basis, then we know that W1 can be written as A11 B1 plus A21 B2. W2, right? Because since W1 is a element in V and these two vectors spans the whole vector space, then I can find weights such that I generate this vector. This one can be written as some two pair of scalars, A12 B1 plus A22 B2, and same thing for W3. This is equal to A13 B1 plus A23 B2. Then we can think about the matrix A. This matrix is a matrix 2 by 3. Let's say this is A11, A12, A13, and here we have A21, A22, A23. But since the dimension of this is 2 by 3, then we know that the null of that matrix is different from the zero vector. That means that we can find a vector x1, x2, and x3 different from the vector 0, 0, 0, such that A times x give us the zero vector. Let me continue here. That means that this system A11 x1 plus A12 x2 plus A13 x3 is equal 0, and A21 x1 plus A22 x2 plus A23 x3 is equal 0. And we have that this x is a fixed, there are some numbers such that are different from 0, 0, 0 and satisfies these two equations. And using this x1, x2, and x3, let's consider this linear combination. x1, w1 plus x2, w2 plus x3, w3. This is equal to x1, and w1 is a11 v1 plus a21 v2 plus x2 times w2, but w2 is a12 v1 plus a22 v2 plus x3 times w3, but w3 is a13 v1 plus a23 v2. And then let's reorganize this, and let me write it as something times v1 plus something else times v2. Then let's see, I have this term here, which is a11 x1 plus a12 x2 plus a13 x3, and for v2 I can factor this term here, a21 x1 plus a22 x2 plus a23 x3. But I know that this part is 0 and this part is 0, and therefore this is the 0 vector, and then the vectors w1, w2, w3 are linearly dependent. That shows that if you have a basis with 2 elements, then no basis can have 3 elements, because those 3 vectors should be linearly dependent. The same proof works in general. Let me just do it. Anyway, I think this one shows more the reason, but let's do the one in general anyway. Then let's assume that we have a basis B, and this basis is B1 up to Bm, and let's consider another set of vectors that goes W1 up to Wn with n bigger than m. And then I will show that these vectors are linearly dependent. Then I will show you this, that if B is a basis, then D is linearly dependent. And then we proceed in the same way. We write every Wi, we can write it as the sum of some weights from j equal 1 until m of a ji v sub j. And therefore, here we have a matrix A. This matrix, which is A11, A12, A M1, A M2, A Mn, A1n. This matrix has more columns than rows, right? N is bigger than M. It means that there are more columns. And therefore, when I consider this system of equations, the system of equations that comes with this, which is a11 x1 plus a12 x2 plus a1n xn equals 0, am1 x1 plus a m2 x2 plus a mn xn equals 0. When we consider this system of equations, we are completely sure that we can find a free variable, we can find a non-zero solution. Then let x1 xn be a solution of that system that is different from the vector 0, 0, 0, 0. And then we will show that this linear combination x1 w1 plus xn wn, which is a non-trivial linear combination because this vector is different from 0. This is equal to, let me write it as a sum, the sum from k equal 1 to n of x sub k, w sub k, and this is just the sum from k equal to 1 until n of x sub k, and this part here is just the sum from j equal 1 until m of a sub j k v sub j, and then since this term x sub k doesn't have a j there, I can move it in and I can switch the order of the sums, and then this is the sum from j equal 1 until m, and then this is the sum from k equal 1 until n of a j k times x sub k times b sub j. But this is just the sum from j equal 1 until m, and each one of these terms is 0. Then 0 times bj, and this is just the 0 vector. That means that these vectors are linearly dependent, and for that reason this cannot be a basis. Therefore, the conclusion is that if we have a vector space and we have two bases, then n must be equal to m.